Hi, I'm Tyler Ehrlich, and I'm part of Group 3. This is our stress strain curve for our aluminum sample in our lab. As you can see, right around 200, you can see the yield point, which is where we leave the elastic region. If you come across the curve to about right here, that's where we have our tensile point. At our tensile point, we start necking. And then if you keep coming across the curve, you'll see the fracture point. The fracture point is where our sample snaps. Our second stress strain curve is for our steel sample. You can see right before 150, it's very difficult, but you can see where you hit the yield point and we leave our elastic region. If you come across the graph to about this area, it's very flat, but it's about this area that you hit the tensile point and you start necking. If you come across the curve, you can see right about here, it's very difficult to see, but it slants a little bit. That's our fracture point where our sample breaks. For our third sample, which was any material we could choose that we were interested in, we chose copper. Now we're going to see part of our third sample, copper, neck right at the bottom here until it snaps. As you can see, it's starting to expand a neck, and then it snaps right at that point. For our third stress strain curve, we have the one for copper. Right here, you can see our yield point, which is where we leave the elastic region, come across the graph to the tensile point, begin necking, and then keep going, and you hit the fracture point, where the copper sample snaps, as you just previously saw.
My name is Andrew Horn. Young's modulus is a measure of elasticity, and you find the measure of elasticity by taking a point before the yield point and dividing the stress over the strain. For aluminum, that is 1,077 megapascals. For steel, it is 1,645 megapascals. And for copper, it is 18,864 megapascals. So to find the yield point, you find the point where the line stops being linear, and for the yield strength, you find what the stress is at that point. The yield stress for aluminum is 1,925 megapascals. The yield strength for steel is 120.8 megapascals, and the yield strength for copper is 252 megapascals. So to find the tensile strength, you first have to find the tensile point. The tensile point is the highest point on the stress strain curve, and the tensile strength is the value of stress at the tensile point. The tensile point, the tensile strength for aluminum is 317 megapascals. The tensile strength for steel is 273 megapascals, and the tensile strength for copper is 339 megapascals. Additionally, the tensile point is where necking begins as the stress strain curve goes down.
My name is Liam Mosier, and I am also a member of Group 3. For ductility, that is a measure of how well the material can take plastic deformation before fracturing. You can measure ductility in two ways: percent elongation and percent reduction in area. These two have very similar formulas because they're both percentages. For percent elongation, you take the final length of the material minus the original length of the material divided by the original length of the material. This will give you a percentage of how long the object has been elongated. For aluminum, we had a 1.13% elongation. For steel, we had a 43.6% elongation. And for copper, we had a 14% elongation. For percent reduction in area, you're going to use the cross-sectional area of the material. First, you're going to take the final cross-sectional area of the material minus the original cross-sectional area of the material divided by the original cross-sectional area of the material. This will also give you a percentage. For aluminum, we had a 58.2% decrease in cross-sectional area. In steel, we had a 70% decrease in cross-sectional area. And for copper, we had a 49% decrease in cross-sectional area. The resilience of a material is defined by how much energy a material can take while being deformed elastically. The formula for resilience is U sub R equals the integral from 0 to the yield point of the stress d strain. But because it is a linear function for that point, you can also write it as the stress at the yield point times the strain at the yield point divided by 2. So over here, I'm going to show you that the resilience is every end of the curve from here to here. Basically, this entire area. For over here, we have the resilience of our aluminum was equal to 5.28 joules per cubic meter. The resilience of our steel was 18.66 joules per cubic meter. And the resilience of our copper was 1.86 joules per cubic meter. Toughness is defined as the ability of a material to absorb energy while deforming plastically without fracturing. Toughness has a formula, U sub T equals the integral from 0 to the fracture point of the stress d strain. However, we can also simplify this to be the stress at the fracture point times the strain at the fracture point divided by 2. Over here, I'll show you basically what this means. It's the area under the curve of the stress-strain curve for everything before the fracture point. So basically, this entire area here would be the toughness measured. So that's why the toughness is usually a very large number. For our aluminum, we had 71,930 joules per cubic meter for our toughness. For the steel, we had 832,525 joules per cubic meter. For our copper, we had 13,295 joules per cubic meter. Here we have our elastic moduli, our yield strengths, and our tensile strengths right now. Additionally, we're going to show you our experiment and how we set it up and how we executed both the aluminum and steel samples.
What it's doing is re-zeroing it and making sure that everything's starting from a zero slate. Now, as the graph starts to populate, you can see the data points start to go, and then you can see the graphs start to go. The graph, if you look at it as the test is going, you will see it eventually kind of start to slow down a little bit, maybe dip down. Once that happens, if you look at your sample towards the center of the sample, it will start to appear the necking phenomena. It's basically going to look like a piece of chewing gum getting pulled apart. And around that point is when you know that it's about to fracture. So.
Now it has shifted from elastic region to plastic region, where you see the curvature changing. Turning point, that's the yield point, and that corresponds to the yield strength. And if you take a closer look at your sample, you'll see that it's become more slim, but the uniform is slim. We don't have necking yet. After you pass through the tensile strength point, you're going to see neck. You can get closer. You can see the details of the sample and at this thing. You can get closer. See the necking? Pass through the tensile point. Sure you have the necking now.
Soon enough, you'll see a faint line start to appear right where it's going to break.
And there is.
Group 4.
So you curve it up a little bit, then turn down, and you see it fluctuates more, the stress curve, than the iron one. Sorry, steel. compare later at your data, you see your steel is having more smooth data than this. I think necking is happening. See?